Biography. Archimedes, the man who revolutionized science in the ancient world. Full documentary. Birth and origin, 287 BCE, 275 BCE. Archimedes was born around the year 287 BCE in the city of Syracuse, located on the eastern coast of the island of Sicily. At the time, Syracuse was one of the most important city-states in Magna Graecia, a term used by the Romans to refer to the Greek colonies spread throughout southern Italy. The city was a vibrant cultural and commercial hub, influenced deeply by Greek philosophy, art, and science. Though geographically distant from the Greek mainland, Syracuse maintained strong intellectual and political ties to the broader Hellenistic world. The historical context of Archimedes' birth is crucial to understanding the forces that shaped his mind. The 3rd century BCE was a dynamic era of transition. After the conquests of Alexander the Great, the Hellenistic kingdoms that followed promoted scientific inquiry and the exchange of knowledge across borders. Sicily itself was a contested space, caught between the growing power of Rome in the west and the established influence of Carthage in Greece. Syracuse, in particular, was governed by a line of monarchs who took interest in learning and supported advancements in knowledge and engineering, factors that would later benefit Archimedes directly. Archimedes was born into a family of status and education. His father, Phidias, was known to be an astronomer and a mathematician. Although little is recorded about Phidias's specific contributions to science, his intellectual pursuits were likely a strong influence on Archimedes' upbringing. In a society where mathematical and scientific literacy were rare, and typically confined to the educated elite, Phidias's profession suggests that Archimedes was raised in an environment that valued knowledge, calculation, and celestial observation. There is no surviving documentation regarding Archimedes' mother, and her identity remains unknown. However, given the customs of the time, it is probable that she belonged to a family of similar social standing. The intellectual household into which Archimedes was born would have granted him access to a private education, rare manuscripts, and frequent interactions with thinkers and artisans. This foundation laid the groundwork for his later achievements. From a young age, Archimedes exhibited signs of exceptional intellect. While most children his age were learning basic arithmetic and memorizing poetry, Archimedes is believed to have been fascinated by patterns, measurements, and the mechanics of physical objects. Stories passed down through generations describe him building primitive models, experimenting with weights and balances, and sketching geometric figures in the sand. Syracuse's wealth and cultural openness enabled Archimedes to observe not only local artisans and engineers at work, but also to hear stories of discoveries made in places like Alexandria, Athens, and Rhodes. These early exposures helped form a mind that was both curious and systematic. Rather than being satisfied with surface-level knowledge, Archimedes was drawn to first principles, the why behind the how. As the son of a respected astronomer, Archimedes was afforded the privileges of elite society in Syracuse. This meant not only access to education, but also the political and social capital to study abroad and later collaborate with powerful figures, including the king himself. His upbringing placed him at the intersection of theoretical knowledge and applied problem-solving, preparing him to eventually revolutionize both. 2. Early education in Syracuse, 275 BCE, 270 BCE. During his formative years in Syracuse, Archimedes received an education rooted in the classical Greek tradition, an approach that sought to cultivate both the intellect and the character of the individual. His early schooling would have included instruction in arithmetic, geometry, astronomy, music, poetry, and physical training. This curriculum reflected the educational ideals of the time, inherited from earlier philosophers like Plato and Aristotle, who believed that a well-rounded citizen should be skilled in both thought and action. The mathematical component of his Education would have focused initially on basic operations and gradually advanced toward geometric proofs, logical reasoning, and the use of mathematical instruments such as the abacus and compass. Archimedes' aptitude for geometry likely became apparent early on. Geometric drawing was more than a technical skill in ancient Greece. It was considered a path to understanding the fundamental nature of the universe. Music, too, played a significant role in Greek education. Far from being a mere artistic pursuit, music was connected to mathematics through ratios, harmonics, and patterns of proportion. It is plausible that this interdisciplinary training helped Archimedes develop an intuitive sense of balance and order that later translated into his engineering designs and physical theories. Astronomy was also integral. Under his father Phidias's guidance, Archimedes would have studied the motion of celestial bodies, the structure of the heavens, and the mechanics of timekeeping. Ancient Greek astronomers relied heavily on geometry to describe planetary movement, and this tradition would have influenced the way Archimedes later approached problems in both mathematics and natural philosophy. Syracuse's place within Magna Graecia ensured that Archimedes was not isolated in his learning. The city was part of a vibrant network of Greek-speaking regions that traded not just goods, but also ideas. The philosophical schools of southern Italy, particularly those connected to the Pythagorean and Eleatic traditions, would have been known to educated Syracusans. These schools emphasized rational thought, abstraction, and the search for universal truths, all values that would later define Archimedes' approach to science. Moreover, Archimedes grew up in a household that provided access to mechanical devices and tools, likely exposing him early to the practical applications of theoretical principles. Artisans and engineers in Syracuse created complex machines for construction, defense, and daily use, and the young Archimedes probably observed their work with fascination. It was common for educated Greek boys to apprentice informally with craftsmen, learning firsthand about pulleys, levers, and counterweights, all of which would later become central to his inventions. Because of his father's standing, Archimedes had contact with members of the Syracusan court and local intellectuals. This proximity to power gave him opportunities to engage in discussions and debates with older, experienced scholars and advisors. Theoretical knowledge in Greek society was held in high regard, but the divide between thinkers and doers often limited innovation. Archimedes, even in these early years, appeared to bridge that gap, comfortable in the world of numbers and ideas, but equally interested in physical phenomena and the manipulation of matter. Greek education often involved a tension between abstract knowledge and practical utility. Philosophers like Plato had expressed disdain for manual labor and technical work, considering them inferior to pure thought. However, in places like Syracuse, where political survival often depended on engineering and military prowess, this dichotomy was less rigid. Archimedes was shaped in this unique context, a city where practical invention and theoretical brilliance were not just compatible, but essential. Academic formation in Alexandria, 270 BCE, 260 BCE. Sometime during his late adolescence or early adulthood, Archimedes left Syracuse and traveled to Alexandria in Egypt, a city that stood at the intellectual crossroads of the ancient world. Founded by Alexander the Great in 331 BCE, Alexandria had grown into a thriving metropolis and cultural capital under the Ptolemaic dynasty. By the time Archimedes arrived, it was home to the Library of Alexandria, the most ambitious repository of human knowledge ever assembled up to that point. The decision to study in Alexandria was not unusual for elite Greek scholars of the period. The city attracted mathematicians, philosophers, astronomers, physicians, and poets from across the Hellenistic world. It offered access to vast collections of papyri, intellectual mentorship, and vibrant scholarly exchange. For Archimedes, the e-apur experience would prove transformative. In Alexandria, Archimedes studied under the intellectual descendants of Euclid, the father of geometry, whose elements had by then become the standard textbook of mathematical thought. Although Euclid himself had likely died decades earlier, his methods and axioms defined the curriculum. Archimedes immersed himself in this rigorous logical framework, learning how to build complex proofs from a small set of assumptions and basic postulates. One of the greatest strengths of Alexandrian education was its commitment to formal reasoning and abstraction. While Archimedes had already received training in Syracuse, Alexandria challenged him to elevate his thinking, moving beyond practical observation to mathematical modeling and systematic exploration. He began to refine a style of mathematical writing that was both elegant and exacting, and which would later distinguish his treatises from those of his peers. In Alexandria, Archimedes came into contact with other rising mathematicians, among them Conon of Samos, who would become a trusted friend and correspondent. Their intellectual relationship was important. In the ancient world, where travel was slow and dangerous, the exchange of ideas often happened through letters, and Archimedes kept up correspondence with Conon even after returning to Syracuse. These letters were not casual. They contained complex geometric problems, innovative solutions, and entire proofs, forming one of the earliest known examples of collaborative scientific dialogue by mail. It was in Alexandria that Archimedes also encountered the interdisciplinary environment that would later define his own work. Unlike modern academic institutions with rigid departmental boundaries, Alexandrian scholars moved freely between fields. Astronomy, geometry, mechanics, and optics were treated as interconnected branches of inquiry. This culture encouraged Archimedes to see patterns across disciplines and to adopt an integrative approach to knowledge. Another important aspect of Alexandrian education was access to experimental instruments and models. The museum complex attached to the library housed tools for measuring angles, distances, and time, celestial globes and mechanical devices, as well as hydrostatic apparatuses. Archimedes, who had already demonstrated an interest in mechanical principles, likely spent time observing or working with these tools, absorbing techniques that would later be incorporated into his own inventions. Though few direct records survive from his time in Alexandria, later evidence suggests that Archimedes used this period to build the mathematical foundations of his most important future works. He began developing ideas about infinite series, methods of exhaustion, a precursor to calculus, and geometric transformations. His style of combining mechanical insight with theoretical deduction was already forming, influenced by both the rigor of Euclidean geometry and the playful experimentation of Alexandrian scientists. When he eventually returned to Syracuse, Archimedes carried with him not only the intellectual riches of Alexandria, but also a deepened confidence in his own ability to extend the boundaries of what was mathematically possible. He was no longer a gifted student. He was a thinker prepared to challenge the assumptions of his age. 4. Return to Syracuse and the beginning of scientific work, 260 BCE, 250 BCE. After spending a formative decade in Alexandria, Archimedes returned to his native Syracuse, a city whose political and military significance had only grown in the intervening years. His homecoming was more than a personal journey. It marked the beginning of a period of intense productivity and creative exploration that would redefine the boundaries between theoretical mathematics and practical engineering. Upon his return, Archimedes resumed close ties with the royal court, particularly with King Hero Send, who ruled Syracuse with the support of Rome and maintained a precarious balance of power in the western Mediterranean. Historical accounts suggest that Archimedes and Hero had a strong mutual respect. Hero, known for his patronage of the arts and sciences, recognized the value of Archimedes' intellect and frequently sought his counsel on matters involving mechanics, fortifications, and problem-solving. One of Archimedes' earliest contributions in this period was the design and refinement of mechanical devices that served both civic and military purposes. Among these, the most enduring was the Archimedean screw, a device created to move water from low-lying areas to higher ground for irrigation or drainage. The mechanism consists of a helical surface contained within a cylindrical shaft. As the shaft is turned, water is lifted upward through the spiral path. This invention became widely used across the Mediterranean world, and variations of it are still employed in modern agriculture and engineering, including in some wastewater treatment systems in the United States. While inventions like the Archimedean screw demonstrated his ability to solve immediate practical problems, Archimedes never abandoned the abstract mathematical thinking that he had refined in Alexandria. Instead, he began to apply mathematical analysis to real-world challenges, a radical move in an era when most scholars maintained a strict divide between theoretical and practical knowledge. King Hero, intrigued by Archimedes' brilliance, often set him complex problems that required both imagination and precision. These included tasks such as calculating the weight and purity of objects without damaging them, measuring irregular shapes, and devising systems to lift enormous weights. With minimal human effort, through such challenges, Archimedes deepened his understanding of levers, pulleys, and statics, the study of forces in equilibrium. It was during this time that Archimedes famously said, "Give me a place to stand, and I will move the earth." This was not mere hyperbole. He had discovered how the principles of leverage could be applied to magnify force. By placing the fulcrum at the correct point and applying force at the appropriate distance, a person could theoretically lift an object of any weight. Archimedes even demonstrated these ideas by constructing cranes and lifting devices capable of moving entire ships out of water with minimal labor. These experiments amazed both citizens and dignitaries, reinforcing his reputation as a man whose knowledge could reshape the physical world. Archimedes also began producing more precise, measuring tools, including devices for timekeeping and astronomical observation. Some sources claim that he built a kind of orrery, a mechanical model of the solar system, that accurately represented the motion of celestial bodies. Although no such device has survived, later Roman writers marveled at his ability to replicate the heavens using gears and mathematical ratios. Despite his royal connections and growing fame, Archimedes maintained a scholar's lifestyle. He avoided political power and rarely attended public ceremonies, preferring to spend long hours in seclusion, immersed in drawings, calculations, and thought experiments. This distance from public life allowed him the freedom to pursue ideas with purity of purpose, ideas that would soon culminate in the creation of some of the most influential mathematical works in human history. In Syracuse, Archimedes was finally in a position where his education, intellect, and social access converged. He had the theoretical foundation from Alexandria, the material support of a powerful ruler, and the curiosity to push beyond the known. Over the next decade, he would write and experiment at a pace and depth that no thinker before him had achieved, setting the stage for discoveries that would reverberate through the centuries. 5 mathematical writings and discoveries, 250 BCE, 240 BCE. The decade between 250 BCE and 240 BCE was a period of astonishing creativity for Archimedes, during which he composed most of the treatises that would later define his legacy as one of the greatest mathematicians of all time. Unlike many thinkers of antiquity, whose work survived only in fragments or second-hand references, a significant portion of Archimedes' original writings endured, allowing modern scholars to appreciate not only his conclusions, but also his methods. Carefully constructed arguments built with clarity, logic, and mathematical elegance. One of his most celebrated works was On the Sphere and Cylinder, in which Archimedes derived the formulas for the surface area and volume of a sphere and compared them to those of a cylinder encompassing it. Using purely geometric reasoning and the method of exhaustion, an early form of integral calculus, he demonstrated that the volume of a sphere is 2/3 the volume of the cylinder that contains it, including its height and diameter. Similarly, he showed that the surface area of the sphere is 2/3 the total surface area of the cylinder, including its top and bottom. These results were not only mathematically correct, but also aesthetically satisfying, embodying the deep symmetry and harmony prized by Greek thinkers. Archimedes was so proud of this discovery that, according to the Roman statesman Cicero, he requested that a diagram of a sphere inscribed within a cylinder be carved onto his tombstone. Though the exact tomb has been lost to time, this anecdote underscores how central the discovery was to his identity as a mathematician. In another landmark treatise, Measurement of a Circle, Archimedes tackled the problem of determining the value of pi, the ratio of a circle's circumference to its diameter. Using inscribed and circumscribed polygons with up to 96 sides, he arrived at a remarkably accurate estimate, proving that P lay between 317, approximately 3142857, and 31071, approximately 3140845. This method, far ahead of its time, required extraordinary precision and patience, and it remained the most accurate approximation of P for nearly a millennium. Equally ambitious was the Sand Reckoner, a text in which Archimedes set out to count the number of grains of sand that could fill the known universe. Though the goal might appear whimsical, the treatise served a serious purpose: to develop a system capable of expressing very large numbers. At the time, Greek numeral systems were limited to relatively small magnitudes. Archimedes broke this barrier by constructing a notation that could express numbers as large as 10, 6, 3, 10, 63, or 10, 63. In doing so, he indirectly contributed to the conceptual foundations of logarithms and exponential notation that would emerge centuries later. In this same text, Archimedes also hinted at heliocentric ideas, the notion that the Earth and planets revolve around the Sun. Though he remained cautious in his endorsement and attributed the theory to Aristarchus of Samos, his inclusion of such ideas reveals his openness to revolutionary models of the cosmos and his comfort with radical speculation when supported by logic and reason. Another essential work was on spirals, where Archimedes studied a curve generated by a point moving at a constant speed along a rotating line. Today known as the Archimedean spiral, this curve had both theoretical and practical significance. He used it to find areas bounded by curves and straight lines, once again anticipating methods that would later be formalized in calculus. The spiral would eventually influence fields as diverse as engineering, physics, and art. In On the Equilibrium of Planes, Archimedes laid the foundation for the study of statics, a branch of mechanics concerned with forces in equilibrium. He introduced the concept of the center of gravity and developed mathematical techniques to determine it in various shapes. This was a breakthrough in understanding balance and structural stability, principles that later engineers and architects would rely upon to build everything from aqueducts to cathedrals. One of the most intellectually daring treatises was Method of Mechanical Theorems, which was lost for centuries and only rediscovered in a palimpsest manuscript in the early 20th century. In it, Archimedes described how he used physical intuition and mechanical reasoning to arrive at geometric results, and then proved them rigorously using formal geometry. This text revealed a hidden layer of his process, combining experimental insight with mathematical proof, a method strikingly similar to the scientific method that would not be formally articulated until the time of Galileo and Newton nearly 2,000 years later. What distinguished Archimedes was not just the accuracy of his conclusions, but his systematic approach to solving problems. He would often begin with a hypothesis or intuitive idea, construct a mental model, test it, using logic and known principles, and refine it until he reached a general solution. His proofs were layered, moving from the specific to the general, and they were meticulously written, often including diagrams and verbal explanations to guide the reader through each step. Through these writings, Archimedes revolutionized the relationship between mathematics and the physical world. Rather than seeing math as a mere abstract exercise, he demonstrated that it could describe, predict, and control the material universe. His ideas laid the groundwork for physics, engineering, and the mathematical sciences as they would later develop in the Western world. During this period, Archimedes was not writing for a general audience, but rather for a small circle of elite Greek scholars who could follow the complexity of his arguments. However, his clarity of thought, precision of language, and passion for discovery gave his work a timeless quality. Even today, students of mathematics marvel at his originality and depth, proof that in the quiet of Syracuse over 2,000 years ago a single mind could chart the frontiers of knowledge with nothing more than a compass, a straight edge, and boundless curiosity. 6. Discovery of buoyancy, the Eureka moment, circa 250 BCE. One of the most famous anecdotes in the history of science, and perhaps the most enduring image associated with Archimedes, involves a bathtub, a golden crown, and a king's suspicion. This is the episode that gave birth to the legendary exclamation, "Eureka!" I have found it, in Greek. Though the story has acquired mythic qualities over the centuries, it rests on a solid foundation of historical plausibility and highlights one of Archimedes' most significant contributions to physical science, the principle of buoyancy. According to the narrative preserved by later Roman writers, King Hero II of Syracuse had commissioned a votive crown to be made entirely of pure gold. Upon receiving the crown, Hero suspected that the goldsmith had adulterated the precious metal with silver while maintaining the crown's original weight. The king, unwilling to destroy a sacred object to verify his suspicion, turned to Archimedes for a non-invasive solution. Archimedes was reportedly perplexed by the problem until one day, while lowering himself into a public bath, he noticed that the water level rose in proportion to the amount of his body submerged. It was this moment, an intuitive leap connecting observation with scientific principle, that inspired him to formulate what would later be known as the law of buoyancy. The principle Archimedes discovered states that any object fully or partially submerged in a fluid is buoyed up by a force equal to the weight of the fluid it displaces. In modern terms, this is the foundation of hydrostatics, a subfield of fluid mechanics. It explains why ships float, why some objects sink, and why the human body feels lighter in water. Archimedes' insight allowed him to determine whether the crown was made of pure gold without altering or damaging it. By submerging the crown in water and comparing the volume of water displaced to that of an equal weight mass of pure gold, he could calculate whether the density matched. If the crown displaced more water than the pure gold, it meant it contained a less dense material, most likely silver. The brilliance of the solution lay in its combination of theory and practical experimentation. Archimedes did not simply guess or reason through the problem in the abstract. He performed a measurable physical test based on his newly discovered principle. This was a rare scientific methodology in the ancient world, where empirical testing was often overlooked in favor of pure deduction. Though modern historians debate the precise details of the incident, including whether the test could have been conducted with the level of precision described in the anecdote, there is consensus that Archimedes did indeed articulate the law of buoyancy in his treatise on floating bodies. In this work, which has survived in part, Archimedes systematically analyzes the behavior of objects in water, distinguishing between those that sink, float, or remain suspended. He identifies factors such as density, volume, and the gravitational force as crucial elements in the analysis of floating equilibrium. On floating bodies is the earliest known scientific investigation of fluid mechanics and remains foundational to the field. It also introduced the concept of specific gravity, the ratio of the density of a substance to the density of water, as a tool for assessing the composition of materials. These ideas continue to be used today in engineering, naval architecture, and even geology. The Eureka story captured the imagination of generations not merely because of its theatrical flair, but because it exemplified intellectual discovery through observation. Archimedes did not find the answer through formal study alone. He found it by paying attention to a physical phenomenon that most people would overlook, and by applying reasoning to turn a simple experience into a general law of nature. In American classrooms today, students are often introduced to the scientific method through this very story. It speaks to the importance of curiosity, of open-minded attention to everyday occurrences, and of the moment when a theoretical insight converges with lived experience. Archimedes' bathtub became a symbol, not just of a single discovery, but of the power of the human mind to find clarity in the chaos of the physical world. In engineering terms, the law of buoyancy made it possible to design floating structures with far greater precision. Ships, docks, rafts, and other vessels could be planned not merely through trial and error, but through predictive models based on mathematical principles. Even today, naval engineers in the United States and across the globe apply these principles in designing submarines, oil platforms, and watercraft of every size. The moment Archimedes stepped out of the bath and ran through the streets shouting, "Eureka!" may or may not have happened exactly as the story goes, but the discovery itself was no exaggeration. It was a turning point in the ancient understanding of physics, a moment when the forces that govern fluids were revealed with Clarity, giving rise to a branch of science that continues to influence technology and exploration across land and sea. 7. Engineering feats and military inventions. 240 BCE, 215 BCE. During the latter half of his career, Archimedes increasingly directed his intellect towards solving practical problems for the state of Syracuse, which had entered a period of political tension and growing military threats. Situated strategically in the Mediterranean, Syracuse was vulnerable to both Roman and Carthaginian ambitions. Archimedes, though not a soldier, became the city's most vital asset in defense. His knowledge of mechanics and physics was turned toward the art of war. Among his many contributions, one of the most widely admired was his development of compound, pulley systems. These devices, based on the principles of levers and tension, allowed a single person to lift immense weights that would otherwise require dozens of laborers. Archimedes used an understanding of mechanical advantage, the idea that force could be magnified through the use of simple machines, to engineer a variety of lifting devices. His mastery of balance, load distribution, and torque enabled the construction of large war equipment and infrastructure in Syracuse. Accounts from Roman historians, particularly Plutarch, describe how Archimedes used these machines not only in workshops but also in demonstrations that left dignitaries stunned. In one famous anecdote, he is said to have moved a fully loaded ship out of the harbor using only a system of ropes and pulleys while seated at a distance, a feat that reinforced his famous assertion, "Give me a place to stand, and I will move the earth." Yet Archimedes' most astonishing applications of mechanical science came during the Second Punic War, which began in 218 BCE. As conflict between Rome and Carthage escalated, Syracuse attempted to remain neutral. However, after political changes, it eventually sided with Carthage, prompting Rome to act. In 214 BCE, a Roman fleet under General Marcus Claudius Marcellus laid siege to the city. What followed was one of the most legendary episodes in the history of military engineering. Archimedes was enlisted to defend Syracuse with his inventions. The Roman assault, expected to be swift, turned into a protracted struggle, in large part due to the devices that Archimedes constructed and deployed along the city's walls. Among these were advanced catapults that could launch projectiles at varying distances and trajectories. Traditional catapults were limited in range, but Archimedes' machines were adjustable, enabling them to target enemy ships with remarkable accuracy, regardless of their distance from the shore. He also designed ballistae, large-scale missile throwers that hurled heavy darts and stones at high speeds. These machines were preloaded and calibrated to fire from behind the city's fortified walls, giving defenders a tactical advantage. Roman ships attempting to land near the city were often sunk or damaged before reaching the shore, making a direct naval assault nearly impossible. One of the most dramatic and debated inventions was a system of giant cranes or grappling hooks, often referred to in modern literature as the claws of Archimedes. These massive devices were mounted on the city walls and used to lift attacking ships partially out of the water and then smash them against rocks or drop them suddenly, capsizing them. Roman accounts, though often tinged with awe and exaggeration, describe sailors being pulled from their decks and entire vessels being destroyed mid-approach, evoking terror among enemy ranks. Perhaps the most mythologized of all his inventions was the use of mirrors or polished bronze shields to focus sunlight and set Roman ships on fire. While modern scientists question the practicality of this method, given the required precision and intensity of light, experiments in recent centuries have shown it might have been theoretically possible under ideal conditions. Regardless of its factual basis, the story highlights the reverence and mystique that surrounded Archimedes' scientific prowess, both among allies and enemies. Archimedes' engineering achievements were not limited to weaponry. He is believed to have overseen the construction and maintenance of defensive fortifications, towers, and observation posts, designed to optimize the line of sight and increase the range of projectile devices. His background in optics and geometry allowed him to calculate angles of incidence and reflection, which would have been useful in aiming catapults and planning line-of-sight defenses along Syracuse's coastal perimeter. Throughout the siege, Roman forces remained stunned by the precision and efficacy of Syracuse's defenses. Plutarch recounts that the Roman soldiers began to fear any contraption or structure protruding from the city walls, assuming every beam or rope was part of another deadly device. Despite being vastly outnumbered and outgunned in terms of manpower, the defenders of Syracuse, led by the intellect of a single man, held out far longer than expected. It is crucial to understand that Archimedes did not view his military inventions as acts of aggression. He was not motivated by conquest or destruction. His writings reveal a man who valued peace and knowledge, who reluctantly applied his abilities to warfare only out of duty to his city. His machines were tools of defense, not of conquest, designed to protect Syracuse from external domination, not to wage war on others. The use of physics in battle was not new, but Archimedes was the first to integrate mathematics into warfare in a systematic and scientific manner. He elevated the status of the engineer from a mere craftsman to a central figure in the survival of a city-state. In doing so, he reshaped the trajectory of military history, paving the way for future inventors and strategists to recognize the profound importance of science in matters of war and peace. In the modern United States, his approach to integrating theory and practice can be seen in institutions like West Point, where military cadets are trained in engineering and physics, and in the Pentagon's emphasis on technological superiority. From missile trajectories to naval architecture, Archimedes' fingerprints are embedded in the very fabric of American defense science. What Archimedes accomplished between 240 BCE and 215 BCE was nothing short of extraordinary. He translated abstract principles into mechanisms of immediate impact, showing the world that a deep understanding of nature's laws could alter the outcome of history. His genius during this period did not reside only in invention, but in the rare ability to turn knowledge into power, a lesson that resonates deeply in both the ancient and modern world. 8. Later scientific contributions, 225 BCE, 215 BCE. In the final decade of his life, Archimedes reached a level of intellectual maturity that allowed him to synthesize decades of inquiry into groundbreaking new frameworks of mathematical and physical thought. These were not mere refinements of earlier ideas. They were pioneering insights that anticipated concepts not fully articulated until the development of modern science nearly 2,000 years later. While his military inventions garnered public acclaim, it was in the quiet solitude of his study, surrounded by geometric diagrams and papyrus scrolls, that Archimedes made some of his most advanced contributions to mathematics and theoretical physics. One of his most remarkable achievements during this period was his treatise on quadrature of the parabola. In this work, Archimedes used a technique akin to modern geometric series to find the exact area bounded by a parabola and a straight line, an area that cannot be calculated using traditional Euclidean tools alone. By inscribing a series of triangles within the parabolic segment and summing their areas, he demonstrated that the total area equaled exactly 4/3 the area of the largest inscribed triangle. The level of abstraction and rigor required for this proof placed him centuries ahead of his time, effectively laying the groundwork for integral calculus, a field not formally developed until the 17th century by Newton and Leibniz. Equally visionary was the method of mechanical theorems, a treatise thought lost for centuries until rediscovered in a 10th century palimpsest in the early 20th century. In this text, Archimedes described how he arrived at mathematical truths by treating geometric shapes as if they had weight and balance, using mechanical intuition to hypothesize results that he would later prove rigorously. This approach was radically unorthodox for its time. While Greek mathematics emphasized deductive logic, Archimedes allowed himself the freedom to explore problems through analogy, approximation, and symmetry before formalizing them. The method revealed Archimedes as a precursor to the scientific method, showing a mind comfortable with combining experimental intuition with rigorous proof. He imagined slicing objects into infinitesimal parts, balancing them around a fulcrum, and using these visualizations to calculate areas, volumes, and centers of gravity. This mechanical reasoning mirrors modern practices in physics and engineering, where intuition and modeling often precede analytical verification. In his treatise Floating Bodies, Archimedes turned his attention once again to fluid mechanics. Building on his earlier work on buoyancy, he explored the conditions under which solid objects of varying shapes and densities would float or sink. He formulated laws for objects floating in two fluids, such as water and oil, and studied how the orientation of irregular shapes affected their equilibrium. These investigations required a precise understanding of pressure, displacement, and stability, forming the earliest known treatise on hydrostatics. One of the most striking features of floating bodies is its use of geometric proofs to describe physical phenomena. Archimedes treated fluids not just as a subject of observation, but as systems that could be described mathematically. His notion of equilibrium conditions for floating objects prefigured later work in naval architecture and fluid dynamics. The basic principles he formulated are still used today in designing ships, submarines, and buoyant structures across both civilian and military applications in the United States and worldwide. During this same period, Archimedes continued to refine his understanding of centroids, the geometric centers of mass for various shapes. He calculated centroids for triangles, parabolas, and segments of circles, providing a mathematical foundation for statics, the branch of mechanics dealing with forces and torques in equilibrium. These ideas had immediate practical relevance, especially in the construction of levers, balance systems, and support structures. His treatment of physical balance was both analytical and physical, a marriage of abstract theory and applied physics. What set Archimedes apart from his predecessors and contemporaries was not merely the quantity of his discoveries, but their depth and coherence. He moved fluidly between disciplines, geometry, mechanics, fluid dynamics, and number theory, creating a unified vision of the physical world grounded in mathematical precision. He proved that phenomena once thought unrelated could, in fact, be expressed through a common language of ratios, surfaces, forces, and transformations. Despite the increasing demands placed upon him as Syracuse faced the threat of Roman invasion, Archimedes remained committed to the pursuit of knowledge for its own sake. Many of his letters to fellow scholars from this period indicate that he still devoted time to posing and solving abstract problems, some of which were intentionally designed to challenge others in his intellectual circle. He treated mathematics as a form of intellectual exploration, a way to reveal the hidden order of the universe. His later work also demonstrated a remarkable capacity for mathematical generalization. Unlike earlier mathematicians who worked with specific shapes or configurations, Archimedes sought universal rules. He was no longer content to solve a single problem. He aimed to develop a framework that could solve an entire class of problems, whether in statics, hydrostatics, or infinitesimal geometry. While many thinkers of antiquity advanced human understanding in narrow fields, Archimedes extended the frontiers of multiple scientific domains simultaneously. His last decade was a period of integration, a summing up of decades of inquiry, experimentation, and discovery. In his hands, mathematics became a tool not just for calculation, but for understanding the very principles that governed the cosmos. This synthesis of insight, logic, and experimentation represents one of the earliest and purest expressions of what we now call science. Long before the establishment of modern institutions or laboratories, Archimedes achieved, through sheer intellect and discipline, a model of thinking that would become the gold standard for scientific inquiry. His last major contributions marked the high point of Hellenistic mathematics, a peak not surpassed until the scientific revolution of the 17th century. In contemporary American education, the name Archimedes still appears in science and math textbooks, engineering programs, and physics lectures. His methods are taught not as historical curiosities but as essential tools in understanding the behavior of systems under force and motion. Whether analyzing the load-bearing structure of a bridge, designing a watercraft, or modeling the behavior of a liquid in motion, professionals across the country unknowingly rely on principles first articulated in ancient Syracuse. As Archimedes approached the end of his life, his thoughts remained focused not on politics or legacy, but on the quiet, persistent pursuit of truth, measured in angles, arcs, and the subtle equilibrium of bodies floating in still water. 9. Intellectual life and personality. Archimedes' intellectual life was one of intense focus, profound curiosity, and striking originality. He was, above all, a man devoted to the pursuit of knowledge, not for fame, wealth, or politics, but for the joy of understanding the fundamental truths that governed the universe. His personality, though only glimpsed through surviving anecdotes and the reports of later writers such as Plutarch and Cicero, reveals a scholar who lived in quiet contrast to the turbulent times around him. Plutarch portrays Archimedes as someone deeply absorbed in thought, so much so that he would forget to eat, bathe, or engage in basic conversation. This was not a matter of rudeness or arrogance, but a testament to the level of immersion and concentration with which he approached his work. He lived, in effect, more in the abstract realm of geometry and mechanics than in the social or political world of his contemporaries. He did not seek public office, honors, or wealth. Despite his close relationship with King Hero II and the prominent role he played in the city's defense, Archimedes never tried to capitalize on his status. In fact, sources suggest that he avoided public acclaim whenever possible. Unlike the philosophers in Athens who taught in public forums, Archimedes preferred solitude, choosing the serenity of private inquiry over public recognition. His most important works were written not for the masses, but for a small group of learned correspondents, often addressed in the form of letters and proofs. One of the most revealing aspects of Archimedes' personality was his love of intellectual challenges. He enjoyed posing difficult mathematical puzzles to other scholars, problems that demanded original thinking, deep concentration, and often unconventional methods of solution. This habit of challenging his peers reflected both his competitive spirit and his desire to push the boundaries of what was known. He was not content with repeating established results. Every problem he tackled seemed to begin with the implicit question, "What if we looked at this differently?" Archimedes' ability to visualize complex problems in space also set him apart. While his proofs were rigorous and logically sound, he often began with visual models and mental diagrams. He would picture curves, spirals, and intersecting planes, then translate those visualizations into mathematical language. This fusion of geometry and intuition gave his work a rare elegance, combining aesthetic beauty with analytic precision. Descriptions of his behavior during the Roman siege further illustrate his singular focus. Even as Syracuse came under assault, Archimedes is said to have continued his work unbothered, drawing geometric figures in the sand as the sounds of war echoed around him. When Roman soldiers eventually breached the city's defenses, Archimedes was allegedly found in a courtyard, fully engaged in solving a mathematical problem. According to Plutarch, when a soldier approached him, Archimedes pleaded, "Do not disturb my circles," unwilling to break his concentration, even in the face of mortal danger. The soldier, unaware of who he was, killed him on the spot, an act that horrified the Roman general Marcellus, who had ordered that Archimedes be captured alive. Whether or not the story is precisely true, it captures the essence of a man so deeply committed to thought that the boundaries between his intellectual and physical realities blurred. To Archimedes, a moment of mathematical insight was more urgent, more real than the chaos and violence surrounding him. Another dimension of his intellectual life was his correspondence with fellow mathematicians. Letters between Archimedes and figures such as Conon of Samos reveal an early form of international scholarly exchange. In these writings, Archimedes presented new theorems, invited critique, and sometimes included hints or partial results to stimulate discussion. This method of communication allowed him to share his discoveries while engaging his peers in collaborative exploration, a precursor to modern academic dialogue. What remains most striking is the purity of purpose that permeated his life. Archimedes did not see mathematics as a tool for utility alone, although he clearly applied it to engineering and military defense when needed. Instead, he approached it as a means of revealing universal truths. In his writings, one finds no appeals to authority, no political arguments, and no self-promotion. There is only the clean precision of logic, the careful elegance of proof, and an unwavering dedication to uncovering how things work. To students in the United States today, Archimedes' life is often presented in terms of a few memorable stories: running naked through the streets shouting "Eureka," moving ships with pulleys, or designing death machines from the city walls of Syracuse. But behind these legends stands a man of towering intellect and exceptional discipline. He did not merely have brilliant ideas, he pursued them with relentless clarity and depth, showing that genius is not just the product of talent, but of perseverance, focus, and an unwavering sense of wonder. His intellectual life, framed by rigorous logic and inspired imagination, stands as one of the greatest models of what it means to think deeply, live simply, and pursue knowledge not for its reward, but for its own extraordinary beauty. 10. Final years in the Siege of Syracuse, 214 BCE, 212 BCE. In the final years of Archimedes' life, Syracuse was no longer merely a prosperous city of culture and trade. It had become a military focal point in the escalating conflict between Rome and Carthage, two superpowers vying for dominance over the Western Mediterranean. As the Second Punic War raged across southern Europe and North Africa, Syracuse found itself in a dangerous geopolitical position. Initially neutral, the city shifted allegiance to Carthage following the death of King Hero II and the rise of a pro-Carthaginian faction in the city's leadership. This change triggered an aggressive response from Rome. In 214 BCE, the Roman General Marcus Claudius Marcellus launched a naval siege against Syracuse, determined to seize control of the strategically vital city. What the Romans did not anticipate was that one of the most brilliant minds in history was living within its walls, and that he would turn his genius toward the defense of his homeland. Though Archimedes was in his 70s, an advanced age, in the ancient world, he was still intellectually active. When called upon by the new rulers of Syracuse, he did not hesitate to offer his assistance. However reluctant he may have been to engage in war, he understood the stakes. The city's survival depended on delaying or repelling the Roman invasion long enough to maintain its independence. Archimedes mobilized his knowledge of physics, geometry, and mechanics to build a suite of defensive weapons and fortifications that would turn Syracuse into one of the most resilient strongholds of the ancient world. His machines transformed the walls and harbors of the city into instruments of strategic brilliance. Roman accounts, especially from Livy and Plutarch, recount the frustration and astonishment of Marcellus's forces as they attempted to breach the city's defenses. Archimedes had designed catapults of varying ranges, capable of launching massive stones, spears, and flaming projectiles with deadly accuracy. These machines were not stationary. They were mounted on rotating platforms and placed at different elevations, enabling defenders to strike targets near and far, on land or sea. He also engineered ballistae, long-range missile throwers that could penetrate Roman shields and armor. These weapons were likely preloaded and operated by coordinated teams, allowing Syracuse's defenders to maintain a continuous barrage. Ships attempting to approach the city by sea were met with such overwhelming force that many were destroyed before they reached land. Among the most fearsome devices described by the Romans were the so-called claws of Archimedes, giant mechanical cranes that reached over the city walls, grabbed enemy ships with metal hooks, lifted them partially out of the water, and then violently dropped them, smashing their hulls against rocks or capsizing them. While modern historians debate the feasibility and scale of these machines, the accounts are consistent in describing their psychological impact. Roman soldiers came to fear any strange-looking structure extending from the city, assuming it to be yet another of Archimedes' traps. The most legendary of all his inventions, though perhaps the most contested by modern scholars, involved the use of concentrated sunlight to ignite Roman ships. Archimedes was said to have arranged polished bronze mirrors or metal plates to reflect and focus sunlight onto a single point, setting enemy sails aflame. While the physics of such a feat remain debated, especially under battlefield conditions, the story speaks to the awe his ingenuity inspired. The siege dragged on far longer than the Romans had anticipated, largely due to these defensive innovations. Marcellus reportedly said that Archimedes' devices made his army more afraid of a geometrical diagram than a battery of catapults. The Roman general eventually changed tactics, moving away from direct assault toward a blockade and attrition strategy. Over time, food and supplies within Syracuse began to dwindle. After nearly 2 years in 212 BCE, the Romans found a way to infiltrate the city, likely through the betrayal of an internal faction. Once inside, the Roman army overwhelmed Syracuse's exhausted defenders. Amid the chaos of the sack, Roman soldiers looted homes, destroyed property, and killed civilians. Despite General Marcellus's explicit orders that Archimedes be spared, reportedly intending to bring the scientist back to Rome alive, the order was tragically ignored. One version of the story, relayed by Plutarch, describes a Roman soldier encountering Archimedes in an open courtyard. The mathematician was engrossed in a geometric diagram, possibly traced into the dust or sand. When the soldier approached, Archimedes reportedly told him, "Do not disturb my circles." The soldier, unaware of the old man's identity, killed him on the spot, either in frustration, fear, or disregard for his orders. News of Archimedes' death reportedly devastated Marcellus. The general, a cultured man who admired Greek learning, had hoped to preserve and honor Archimedes as a symbol of Syracuse's intellectual grandeur. In later Roman accounts, Marcellus is depicted as mourning the loss deeply, offering a respectful burial and ordering that Archimedes' tomb be marked appropriately. The tomb itself, according to Cicero, was located on a hill outside the city and bore the image of a sphere inscribed within a cylinder, a visual representation of Archimedes' favorite discovery, that the volume and surface area of a sphere are 2/3 those of its circumscribing cylinder. Cicero claimed to have rediscovered the tomb during his time in Sicily centuries later, though its exact location has since been lost. Archimedes' death marked not only the end of an extraordinary life, but also the fall of one of antiquity's most vibrant centers of learning and culture. The siege of Syracuse was a turning point in the Second Punic War, giving Rome strategic control over Sicily. But for those who valued knowledge, science, and the peaceful pursuit of truth, the loss of Archimedes was a far greater tragedy. He died not in a palace or temple, but in a moment of perfect symbolic clarity, surrounded by the very figures that had defined his life, killed by a world unable to recognize what it was destroying. It was an ending befitting a thinker whose mind had soared far beyond the politics of his time, a man who had spent his life measuring the universe, and whose final thoughts, even in the face of death, remained fixed on the elegance of a mathematical line.